Good day, math buddies! Sir Sherwin here, your math instructor. For today's video, we will be discussing all about geometric mean and series. Of course, we'll be guided with these objectives. First, insert geometric mean in the sequence. Second, find the sum of the finite terms in a geometric sequence and find the sum of an infinite terms in a geometric sequence. First, let's define geometric mean. Terms m sub 1, m sub 2, ellipsis m sub k between two numbers a and b such that a, m sub 1, m sub 2, ellipsis m sub k, b is a geometric sequence. Example, 5, 20, 80, 320. Here, 20 and 80 is known as a geometric mean. This states that term between any two non-consecutive terms of geometric sequence is known as a geometric mean. Please bear in mind this one. The geometric mean between any two positive numbers, a and b, is the square root of their product. The geometric mean may be positive or negative. The positive geometric mean of a and b is square root of the product of a and b, while the negative geometric mean of a and b is a negative square root of the product of a and b. Example, insert 3 geometric means between 2 and 1,250. Here, the third term in the sequence is the geometric mean of 2 and 1,250. To solve our third term, that is, third term is equal to the square root of 2 times 1,250. The product of 2 and 1,250 is 2,500, and square root of 2,500 is 50. This means the third term is 50. Let's also remember that the second term in the sequence is the geometric mean of 2 and 50. This means to solve for our a sub 2, that is, square root of 2 times 50. The product of 2 and 50 is 100, and square root of 100 is 10. This means our second term in this geometric sequence is 10. Let us also put into mind that the fourth term in the sequence is the geometric mean of 50 and 1,250. To solve for the fourth term, that is equal to the square root of the product of 50 and 1,250. This means 50 times 1,250, that is 62,500. Therefore, the fourth term in this geometric sequence is equal to the square root of 62,500, which is 250. So to complete our sequence, we will have 2, 10, 50, 250, and 1,250. And the geometric means between 2 and 1,250 would be 10, 50, and 250. Another example, let's insert 3 geometric means between 2 and 20,000. In this case, let's bear in our mind that the third term in the sequence is the geometric mean of 2 and 20,000. So let us solve first our third term. That is equal to square root of 2 times 20,000. Product of 2 and 20,000, that is 40,000. So third term is equal to square root of 40,000, which is equal to 200. So 200 will be placed on the third term of our sequence. Then let's solve for our second term, wherein second term in the sequence is the geometric mean of 2 and 200. So second term is equal to square root of 2 times 200, and that is equal to square root of 400. So second term is equal to 20. And for our fourth term, let's remember that it is the geometric mean of 220,000. To solve for our fourth term, that is equal to square root of 200 times 20,000. So fourth term is equal to square root of 4 million, and that is equal to 2,000. This means that the geometric form has terms 2, 20, 200, 2,000, and 20,000. This means the three geometric means between 2 and 20,000 are 20, 200, and 2,000. Let's define also geometric series. It is the sum of terms of a geometric sequence. There are two types of geometric series. First is the finite geometric series, and the second one is the infinite geometric series. Let's discuss first finite geometric series. It has a formula. S sub n is equal to a sub 1 times the quantity 1 minus r raised to n all over 1 minus r. Or S sub n is equal to a sub 1 times quantity r raised to n minus 1 all over r minus 1. Where R is the common ratio provided that R is not equal to 1. Our S sub n is the partial sum of our geometric series. A sub 1 is the first term and n is the number of terms. Let us have our first example. Find the sum of the first 10 terms of the geometric sequence, -2, 6, -18, 54 ellipses. In this given sequence, first term is equal to -2, ratio is -3, and the number of terms is 10. Substitute these values in our existing formula. S sub n is equal to a sub 1 times the quantity 1 minus r raised to n all over 1 minus r. Substitute a sub 1, which is -2, ratio, which is -3, and number of terms, which is equal to 10. Then simplify. S sub n is equal to -2 times the quantity 1 minus 59,049 is a result when we raised -3 to the 10th power all over 1 plus 3. S sub n is equal to -2 times the quantity 1 minus 59,049 all over 4. Then simplify 1 minus 59,049, that is S sub n is equal to -2 times the quantity -59,048 all over 4. In this case, -2 and 4 can be simplified, and that is they are both divisible by 2. Then S sub n is equal to 59,048 all over 2. S sub n therefore is equal to 29,524. This means that the sum of the first 10 terms of the geometric sequence is 29,524. Another example. Find the sum of the first 12 terms of the geometric sequence 5, 15, 45, 135 ellipses. Again, first term here is 5, ratio is 3, and the number of terms is 12. Substitute this in our existing formula. S sub n is equal to a sub 1 times quantity 1 minus r raised to n all over 1 minus r. Here, S sub n is equal to a sub 1 is 5 times the quantity 1 minus 3 raised to 12 all over 1 minus 3. Simplify. S sub n is equal to 5 times the quantity 1 minus 531,441 all over -2. 531,441 is a result when we simplify 3 raised to the 12th power. Then, S sub n is equal to 5 times the quantity -531,440 all over -2. -531,440 is a result when we combine 1 minus 531,441. Then, we can simplify -531,440 and -2 because they are both divisible by -2. Then, the simplified form becomes S sub n is equal to 5 times 265,720, which leads us to a result of 1,328,600. Let's have another example. Find the sum of the first 15 terms of the geometric sequence 9, 18, 36, 72 ellipses. Again, our first term here is 9, common ratio is 2, and the number of terms is 15. Utilizing this value, substitute this in our existing formula. S sub n is equal to a sub 1 times quantity 1 minus r raised to n all over 1 minus r. Substitute, a sub 1 is 9, common ratio is 2, and the number of terms is 15. Then simplify. S sub n is equal to 9 times the quantity 1 minus 32,768 all over -1. 32,768 is a result when we simplify 2 raised to 15th power. Then, combine 1 minus 32,768, that will lead us to -32,767. Then, let us simplify. S sub n therefore is equal to 9 times the quantity 32,767, which leads us to a product of 294,903. This means that the sum of our first 15 terms in our sequence 9, 18, 36, 72 ellipses is 294,903. Let's also discuss the infinite geometric series. In this series, our formula to be used would be S is equal to a sub 1 all over 1 minus r. It is also known as the sum to infinity, where r is the common ratio provided that absolute value of r is less than 1. S is the sum of an infinite geometric series, and a sub 1 is the first term. Let's have our first example. Find the sum of the infinite geometric sequence 1, 1/2, 1/4, 1/8 ellipses. In this sequence, first term is equal to 1 and the common ratio is equal to 1 half. Utilizing our formula, S is equal to A sub 1 all over 1 minus R. Substitute our first term, which is equal to 1, and our common ratio, which is equal to 1 half. Then simplify. S is equal to 1 all over 2 minus 1 over 2. S is equal to 1 over 1 half. Rules in dividing fractions, all we need to do is to get the reciprocal of our denominator and proceed to multiplication. This means this series can be determined if we will multiply 1 and 2 over 1. In this case, sum of our infinite geometric sequence is equal to 2. Another example. Find the sum of the infinite geometric sequence 3, 2, 4 thirds, ellipsis. In this sequence, first term is equal to 3 and the common ratio is 2 thirds. Utilizing again our formula, S is equal to A sub 1 all over 1 minus R. Substitute our A sub 1, which is 3, and our ratio, which is 2 thirds. Then simplify. S therefore is equal to 3 over 1 third. Again, rules in dividing fractions. We will get the reciprocal of our denominator and proceed to multiplication. In this case, the sum of our infinite geometric sequence is equal to 9. Let's have another example. Find the sum of the infinite geometric sequence 1/10, 100, 1000, and 1/10,000, ellipsis. Again, first term here is 1/10 and the common ratio is also 1/10. Utilizing our formula, S is equal to A sub 1 all over 1 minus R. So substitute our first term and our ratio, then simplify. S therefore is equal to 1/10 over 9/10. In this case, sum of our infinite geometric sequence is equal to 1/9, or we can have it in terms of decimal, which is equivalent to 11 hundredths. This time it is your turn. First, insert 3 geometric means between 7 and 252. Second, find the sum of the n terms of the geometric sequence given A sub 1 is equal to 7, R is equal to 2, and N is equal to 13. And third, find the sum of the infinite geometric series 8, 6, 9 halves, 27 over 8, and ellipsis. There you have it. Hope you learned something new today. God bless us all.